Welcome to the afternoon session of Si2's room. Today we're going to talk about special interest groups, and these are being revved up in 2017, and we're going to see, just what type of interest we have in special interest groups, and in this particular one, we're going to look at experts at the table. That is, how we get people to work together to solve the complex design problems that we're seeing in our designs and the new processes in trying to get from a chip into a package into a board. And we have some excellent experts here that are going to share with you some of the problems that they've had to deal with and bring their expertise in and be able to discuss some of those problems. So a major thing you have to look at is what type of issues are causing major problems or a major impact on you getting your chip to market. If you're not able to get your chip out in April, guess what? You've missed Christmas, and Santa Claus doesn't come to visit you, because your chip can't be designed in without getting out that early. But if you've got problems that can't be solved by your team or can't be solved in a timely manner by your team, you have the advantage of working in collaboration with other people to solve those problems. Some of these experts have seen those problems before and have a solution, and that's all about what special interest groups are about. So you are not alone in those problems. We've seen them before. Wrong way, okay. Si2 is an R&D collaborative. We are focused on design automation. We're member-driven. The members decide what we want to do. But the nice thing about it is we are a group that can protect you from antitrust lawsuits, collusion lawsuits, and because we're a industry-wide group, we can come up with interoperability solutions that cover a lot of ground and come up with it very quickly because we have a wide variety of experts giving input. So our architecture, we're set up in kind of 4 columns. The first column is special interest groups, and this is our incubation group where we sit and discuss problems. Sometimes it's sit and discuss them over a beer. We identify the opportunities. We may do some other things I'll talk about in just a minute. Then we have our working groups, and these are our development groups, usually tied to a particular set of problems. They develop and create the libraries that we support. We have the coalitions, the Open Access Coalition and the Compact Model Coalition, and these are the production software that we support. And finally, added this last year was our university program, and the university program gives us a chance to mentor university students and bring them into the EDA industry and connect them up with potential employers in the future. So what is a special interest group? This is a group that gets together to talk about design problems. We're looking at the same issues. I've been in this business for a long time, and in fact, for longer than most of you have been alive. And when I worked at Cadence for 17 years, I got to visit hundreds of companies, and everybody thinks their problems are unique. Well, they're not. They're just variations on the same problems. And the whole idea behind a special interest group is we are sharing the knowledge that we have. I have an expertise over here. Sue might have expertise over there. Tom has expertise over here. and Corey has a different set of expertise, but we all come together and we share that knowledge, and we come up with unique solutions that then we can customize for our own company's needs. We have both long-term and short-term efforts. So we can have a long-term SIG, like the PDK SIG will probably be a long-term SIG, whereas some of the other things that we're going to be looking at later might be shorter terms. And it's all under the Si2 protections. Our architecture, it starts like this, and what happens is with Si2, in this case, the power users decide, well, we need to have a project done. We need to develop some software and put that into a library, and we can do that with by using the open standards groups or the working groups. From the working groups, we may call upon some of the interns to actually do the coding. So you're getting some free coding there if you're working with the working group. And that might feed back into one of the coalitions, so we add more capability into the base products. It's not hard to imagine that the different groups will work with each other. There will possibly be shared members in these groups. And then the output is going to be all sorts of things, including conference papers. And we can work with other groups outside of Si2, such as the IEEE or the ACM. And we have done that in the past. So what can we do as a SIG? We can investigate, we can analyze, look at problems, and do some market analysis. Of course, discussion is always about collaboration. What we've done in the past is do mainly architecture, where we could come up with a set of requirements. We make some white papers. We present on panels. But included in that is the ability to do some small prototyping. If it's going to become a big project, we want to move it over to a working group. But inside of a SIG, we can do some small prototyping. And then on top of that is training. So today we have 4 experts, or 3 experts and me, and they're going to each share their experience with with problems that they've had, and you can see if those fit your experiences, and some of the things that this special interest group can do to help. And let me get my glasses, because I can't read this. Although I've known Sue Strang from IBM, I've known her for a long time. we were very young when we met. Sue's been a member of the IBM research team up there in Burlington, Vermont, primarily focusing on PDKs. And she's still at IBM, even though most of the PDK people went to Global Foundries, and has had 20 plus years in the PDK development area. And Corey Krug is a local guy, originally from Oracle, but is now at Samsung, and he'll be talking about the open access scripting language. Corey has been very active with Si2 and has been active with the development of open access and OA script. And Tom Whipple comes to us from Zuken and has been active with Si2 in the chip package co-design, and is presenting on whatever. Okay, so let me call Sue up here, and Sue, if you want to come up. There you go. And I don't know if this will work or not. Yes, it does. All right. And that's your laser pointer right there.
Okay, just thank you, Ted. As Ted said, that I'm with the IBM Corporation Group up in Burlington, Vermont. Actually, I'm working out of the Albany Nanotech on advanced nodes. And for many years, I was working on the Pdk, the foundry Pdk support when IBM, owned the manufacturing, but it has since diverged to Global Foundries. So I really feel as though this is a very good time to be in the CAD business, because when we first started out with PDKs, it was IBM technology and IBM designers and IBM tools, and it was all just the same thing. A person talking to a person talking to a person was all in the same row. You didn't even have to get out of your desk. You could shout down the hallway, about different problems. But as IBM's Foundry grew and we became a foundry for different companies, we found that we had to create a PDK. We had to create some sort of design system in order to get our technology to our design teams. Now, whenever I'm working in research, but the foundry is in a different place, the EDA vendors are in a different place, and the designers are in a different place. So you've got this triangle, and this triangle and the communication between the different legs of the triangle are becoming more and more strained. And I really feel as though the time is ripe right now for us to really do some collaboration and really focus on an open PDK. That'll make it easier for all of us to get down to what we really want to do, is innovation in CAD and innovation in designs. So what I'm going to talk about a little bit, I'm going to start with who we are. So there's a lot of CAD teams within IBM. I am part of the research one, but our team focuses on IBM systems and the fabless designs and the support for that team. They have their own huge CAD team, but I work with them on a device level with helping them out with their designs. Our biggest focus is the Nanotech research for emerging technologies, and I don't know if you've seen in the VLSI symposia about 2 weeks ago, IBM announced the 5 nanometer support in the nanosheet technology, and that is something that my team's working on. But we also are support for design teams for research missions, including cognitive computing and different types of memory and storage and machine learning based tooling. So really it breaks up into, we work on a product design and we work on, research designs. So the challenges for research are twofold. One is EDA focused. So EDA tools are developed for mainstream applications. And so when it comes to research, we find that we have different needs that cause us to be creative with what we get from your basic EDA companies. And so we have to have kind of code in between what they support, or we have to work with them in order to establish new methodologies for some of our technologies, some of the parasitics and some of the devices that we are using in our Albany Nanotech foundry. And so, and we develop a lot of custom tools. One in particular is a 3D rendering of structures that we use to identify the stack up, the whole stack of the new technology, and we find out where the parasitics are, and we have a link from that into a parasitic generation tool. We do pad set generations for our test chips and custom place and route for our macros that are going into the test chip of for the technology. So the custom layer for 3D viewing, that is an IBM tool that we are integrating into Synopsys and Mentor LVS and STAR parasitic extraction. We also have this macro placement and wiring system. So these are the pad, I guess. Oh. So these are the pads. Oh, hey, you big thumb. Sorry about that. Okay. Ugh. Here are the pads here, and this is the macro for our test chip where we're testing the different devices that we're putting in new device architectures, and then there's an automatic wiring up to the pads. We have integrated EDA flow, and we have to make specialized technology files, parameter cells, and interprocess calls into our custom tools. So what are the challenges that we face? So different process constraints, and so these are the tools. For our custom tools, we have process constraints, and the challenges is advanced processes are not supported, and with the mainstream vendors, we have to talk with them, and many times we can't even talk with them because it's we don't have a disclosure in place that we can talk with them, so that we have to use our own judgment and our own updates for those functions. Design rule manual to import layers and rules. That requires the rules to be in a rigid design rule manual format, which we don't typically have with these very early mature technologies. We usually have just like, back of the envelope, and they change all the time, so we have to do that custom. Waveform integration, diagnostics and integration. So we have different simulator tools that we have to import in, and we want to look at our waveforms in our custom tools. So it's back and forth with a lot of these tools. Customized net listing. There are no lack of built-in functionality in EDA just to do a plug-in of our customized net listing. Pad set generation, auto wiring. We talked about before. The scripting is based on EDA database structures, and it's inconsistent between vendors. We have to change whenever we change, and we're looking at a different vendor. Interprocess communications, database translation, test case generation, because every time the EDA company puts out a different version, we have to test it to make sure that we can still operate our custom tools the same way. One of the biggest one is single source verification code. We have several different verification tools, and we want to write the code one time, and it's you can translate some of it, but not all of it. And then, of course, there's the viewing and the sign-off. On the other side of the business, talking about the challenges of a fabless PDK development flow. So we customize the EDA tools mainly for our research tooling, and somewhat for the product design. But for the product design, we also change the PDK development flow. So we may have multiple foundries. We might have, and different nodes, 14 SOI or 14 bulk, or we might do the 16 nanometer. So we have to be able to take our designs and go from fab to fab, from node to node. And there's varying EDA support with each one of these fabs. One may be a Mentor house, one may be a Synopsys house, one may only support HSPICE models, one may only support Spectre models, one may just support K-layout. And then there's methodology and customizations that we do on all of our tools. So this customization is also on the product side. One topic in particular I want to talk about is like integration of a custom device into a technology. So the technologies that we get from our foundries don't always contain, we need to add our customer devices that we have for EDA, ESD protections. And namely, this particular one is one that I have to define this every time there's a new PDK that we're getting from a vendor. And this is a tunable inductor that we put together. It's like two inductors on top of each other, and they're tunable by stripping off each one of these segments. And it's and there's a center tap, and there's different tapping, whether you're from the center, from the top, from the bottom, or the side. And the coil itself is variable, one layer, two layer, coupled, or three different layers with that. So every time the PDK vendor changes, I have to create this again. So for PDK customization, it's very similar to our EDA customizations. Adding layer additions, we have to get our foundries to give us certain layers. Importing of the design rule manual rules. Different foundries have different formats. Integrating PDKs into a custom P-cell, as I was saying, we have to change that every time we get a new version. Standard cells, putting together our own standard cell libraries and hierarchical cells. It depends on how those devices are done within the PDK of the foundry. We have to change that based on every time there's a different PDK device, we have to change our standard cell library to match that. Device parameter manipulation. We'd like to have a reuse of PDK parameter checking, and it's different for different PDKs. Back in the line and verification. PDK structures are not, they're not really set up to support custom structures, so we have that custom tunable inductor. We have to black box it in order to put it into LVS, and it's different for every technology. So there's a lot of similarities and differences between the EDA updates and the foundry updates, but that's the two parts of that triangle, and with the design house being that third part. So how will an open PDK special interest group help? It's interesting. So I was listening to Joe. I don't know if everybody went this morning, but Joe Costello was giving the keynote talk this morning on Internet of Things. And he was saying that the Internet of Things is really diverse. And he said, and through that diversity is coming collaboration. And I think that's very, very similar in PDKs, because it's becoming very diverse. The foundries are becoming diverse. The EDA companies are becoming diverse, and the design companies have always been diverse. So really, through that diversity, our collaboration with each other is going to be how we're going to get that open PDK standardization easier to implement our own solutions into that open PDK, and not have to worry about some of the small stuff, right? And IBM's EDA and PDK challenges are not unique, which means everybody's had to put in their own custom devices. Everybody is interested in a single source verification code. And the absence of standard methodologies and flows by EDA industry really do force customization for all of us. And customizations require in-house CAD support. So every team that has to do any of this customization has to have an in-house CAD support. And the validation and regeneration of customization required for each PDK in EDA tool. It's just becoming it's becoming a lot of work. And really, if we have the standardization, we can get rid of some of these issues that we're all facing. So the benefits of an open Pdk special interest group is collaboration, as Ted was saying, collaboration and standardization. It will force a change in the industry. It will force, it will force innovation in other ways instead of, us all doing the same thing in each different company. Standardization of technology and device information leads to better syncing of designs and manufacturing. So, if everything's standard and you're porting one design from one fab to another, and the fab is looking at developing those, your designs become more robust through standardization. Various solutions, best practices. Si2 is in a great position to recommend flows, language, syntax, translators. As Ted was talking, they have that academia leg that could really assist with a lot of these standard tooling. And participation will expand viewpoint and combine knowledge because, I don't profess to having the best methodology. I mean, there's somebody else that might have a better methodology. And so with this diversity, we can find a better solution. And our Open Pdk is well aligned with our design goals of design enablement and design manual automation. Automation is really paramount for a lot of these companies, for a lot of our company in particular, and Open Pdk will really help us align to that. And that's all. Thank you.
All right, let me. Next up is Corey from Samsung. Come on up here. There you go. Arrows, and then the red is the laser.
Okay. Hi. So I was asked to put together a small presentation for this SIG meeting. I decided to go with the Troublemaker's Guide to Si2 Open Access. One of my colleagues last year here at Snug in the hallway said, I wish we could get enough of us troublemakers together to make a DAC panel. And he was kind of talking about the same sort of thing that we do in terms of what we do at companies. So, my idea of what he meant and what I feel is troublemakers often in physical design or CAD teams, so we're kind of at the end, we're trying to make silicon with these tools. We're solving issues with flows, tools, libraries. We just need to get everything working together. And someone that's just interested in OA for the capabilities it adds. They don't have a projected target when they start out, they say, but this is wonderful for what I need, for debugging, for checking my libraries stuff. And that's kind of a different use from OA script than what the EDA companies do. They have a targeted platform. They want to build their tool on top of OA or OA script. And we're more towards small targeted, 1 or 2 day projects, solutions. And then often we're converting data between different vendor tools. Other vendors don't really think about that unless they're trying to get in the market. Where we're handling data, we need to transfer data from one tool to another, from Synopsys to Cadence, for example, or something like that. And OA's a wonderful thing in between. So I'm going to kind of go over today to just kind of some steps that come into Troublemaker. So first is you find your company's OA script environment or build your own. I have some tips along the way of if you have to build your own. You need to set up your library and technology files, and then you just start solving problems, finding solutions, and ultimately just find ways to tape out a better design. So a little bit of my background. So I spent several years as a design engineer. Had a slightly different database system, but it was analogous to open access. it started off as modifying Perl TK cell viewers for just small projects and stuff. We had a common viewer. You could just modify it for whatever you needed. I ended up implementing a clock gating algorithm within that Perl TK viewer to show how it works. And then started gathering data for design improvement task force. That kind of moved me on to more of a sign-off role, static time analysis. I didn't do as much OA then, but then I moved back into a CAD methodology development role. So I started building a physical design flow for a small CPU team. I built my own OA script, PyQ25 cell placement viewer. I did a hybrid schematic synthesis flow with Cadence Virtuoso to Synopsys DC. I presented that at SNUG conference a few years ago. And then in Virtuoso, one of my biggest projects was I automated a libcell view changes through menus, and that's going to, I'll show you that later. In addition to that, when I moved on, I started joining the OA script working group. I joined that in about 2010. With that group, I've added Python 3 support, and then I've done a lot of helps with the documents and the forums for that group. So a disclaimer, just avoiding real trouble. Learn and follow your company's policies. Licensing, downloading, sometimes you may have to actually get with your manager and push licenses through and get with the lawyers, make sure you have the ESG license or the appropriate open access license. Open source licenses, you'll be doing open source tools. Understand that. Just make sure you play within the rules and you don't get in trouble with your own company. In addition to that, handling and security of library data. You may have third-party libraries, vendors. They may restrict access to it. You don't want to compile data and sit it somewhere else. That's not appropriate. And then, of course, also communications copyright. When you ask questions on forums, when you submit code patches, other stuff, you may have to go through certain approval processes. So just make sure you stay within your own company's rules, but otherwise you can make as much trouble as you want. So set up your environment. I recommend you create your own install area. Basically, you will be generating compiling lots of open source tools, and they're honestly ancient versions of tools. You don't want to overwrite, even if you have root access, the current versions of your tools. Create a little home directory, installs, something like that. And this allows you to install the tools to help you compile open access OA script and the leftdef package involved. GNU.org, that's where you'll find most of your packages. Bison, zlib, GCC 4.2, they're somewhere around 6.3 or so now. And basically most of these work, you just download the package, unzip it, and then configure -prefix to where your installation area is. Make install. Most of them just work that way. It's very common. You'll get used to that, and it'll be pretty regular. Flex 2.4. This is an ancient version of Flex. They moved hosting providers. They seem to have lost that pretty much. According to OA forums, they're working on updating the parsers and stuff, and so that may be in an update sometime soon. I haven't had direct contact with them. But that one may be the most problematic right now. Si2 on their site has a leftdef package. You have to go find that, search it out on the Si2 site, build that, merge them together, and that's also part of it. And there's a document with open access that goes through all the setting up of these and what versions are required. One thing that I've done recently when I did it, I skipped the OA Tickle compile. There's an OA Tickle built into open access. That's superseded by the OA script Tickle. That requires Tickle 8.4. It's not on your system anymore. I wouldn't deal with that. I would just go into you have to find it in the make files and comment it out to just not build that. And then finally, if you want, you could just download Si2's binary images. They'll have certain versions available, but you don't learn nearly as much with that. And also, compiling your own helps you get into OA script a little bit further. So that was kind of the keys, and so you compile that, and then the OA script is very similar to the OA, except you just need to point to your OA source, deal with the small make file. Once you have everything built, then you need to start making libraries. And the first thing you start with is the tech lib. So your Foundry usually provides a Virtuoso TF file for all the layout personnel to use. So you need to start with that. But often is the case, your standard cell library has the vias that will be used. I dealt with a third-party library. They actually had different vias for the different Synopsys versus Cadence routers. And so you may have to convert between those. And so you want start with your Foundry's technology file. You delete all the vias from the Foundry. You put in all the vias from your library. And you create a unit cell. I actually put a long time ago, put a tutorial up on that, showing you how to do that through the Cadence Virtuoso tool, and also through an OA shell script. Then after you have your technology file, you can start creating your own libraries. And so you start turning your standard cells into libraries. Left to OA, we'll create abstract views. Stream to OA, we'll create layout views. And then symbol views, you may or may not get them from your library provider, and then you kind of want to merge those in to make everything work together. And also at some point you can write OA script to modify the views to how you need them also. After that, you have libdef files, just specifies a list of all the libraries involved. And then the key test is once you start doing verilog to OA or def to OA of current designs, errors or warnings will let you know if you're missing vias, if you're missing cells, if you're missing any components. So just watch errors and warnings on that, and if you can get through clean, then you're usually pretty good on that, and you can just start using it for scripting purposes. So this is just a couple examples of useful things you can do, suggestions. First is kind of starting out. So Python is a favorite. One of the key things, it has a good shell for debugging and development. There's so many times when I'm doing something, I open a Python shell, I open my design manually, and I'm just typing in manually. I'm not doing scripts. And then I cut and paste that over into my script and once I get it working. It has a good shell for that. It's much better than Tickle, and you can do a lot with that. Also, it's the most commonly used, and it's best supported by the working group. The Python. Ruby is probably second, followed by Perl, then Tickle in terms of the languages available. I highly recommend this, and this is one thing I did when I first started, was I wrapped the common OA classes with my own classes. They're analogous. I just changed the interface. So the libraries, the design, the inst, net term, inst term. You can even change the names to what your company calls these things. If it's not an inst term, it's a pin at your company, you can change the name to pin if you like. And that helps you create an interface that acts like standard Python libraries. The wrapped Python acts like C++, and it acts like the static function C++ that's how the style that they used. And so you can make things work a lot more operator-oriented. And the other thing is, once you start wrapping the classes, it becomes easier when you're in the Python shell. And I'd also add to this a pretty print function to print out the cell, the status, the placement, the coordinates, things like that. Because once you're debugging, you want to be able to, just within the shell, understand what the status of that cell, or as you're iterating. And then the other thing I did with these libraries was you hide the harder concepts of OA. Getting read access and write access, and you have to trade one for the other. You can't have both at the same time. All that, it's just best to do this in functions, and then you can do them once right, and then you don't have to worry as much about it. And you don't have to worry about it when you're in the shell, getting read and write access. The create, find, static, get class functions, you can just make that into your, I have some examples in the next page. And then other things like when you get a pin, well, in OA, when you get a pin, first you get a term, then you get the figs, then you get the pins of that, and you can kind of just compress that all into a single concept and just simplify everything. based on how you do it. And also, when you're trying to operate on a net, you actually need Python. You need to operate on every equivalent net and not work on just that net, because it could be multiple hierarchies across that net. So these are all things that it's just easier if you hide them in a net class, in your design class, in your library class. And of course, automation, once you have that, you can also do some very complicated things with setting up new library directories, and then more complicated things like, you copy and remaster a whole library set from one library to another. So this is an example of just kind of writing your own class. And so, one of the things is, we have the init function in Python, which is when you create a new object, and basically it's like you can either pass in an instance, it wraps it, passes it back itself. Otherwise, a string, then this is an example of calling a static function to find. Basically, with a string, you need to get a block, and then it will actually just go and query for that OA inst, and then give the object back with that in it. Another example is when you get something like a get placement status, it passes back a real object, but it's easily converted to an int, and you have to do that to convert to these OA placement status. And it's just easier to capture this all in one big group as just a simple function. Then it works forever for you, and then you can also hand this library off to other scripters. And another thing, just another example. So input pins. This is just a case of filtering as you iterate over pins. You just want to get a certain type, and then you can create a new generator here, and that just just simplifies everything along the way. Also, I'd note that there's a lot of error checking you probably want to do. This code is just highly simplified, removed most of that, but you want to check, simplify it for yourself in debugging later. Check your own errors. Check if this is blank, then throw the proper errors, so you're not working on a none object or anything like that. So after this, I kind of highlight a kind of a more complicated project. This is a sort of level project, or this is sort of level trouble you can get into. And actually, I have to give a little credit. Ted originally kind of inspired this a little bit because we had lunch once. He wanted me to work with P-cells and OA script and provide a function. And kind of at the time, I was working with schematics and symbols and stuff at the same time. But it's like, okay, how would schematics and symbols map to a P-cell-ish sort of function? And well, the idea is within Virtuoso, if you want to change your cell name, you have to go into your library name, and you have to retype a new library name. And you have to go retype a new cell name, and that has to be correct, or it will reject it. But through OA and through parsing all the libraries, so iterate across all my libraries, I can create this little box here that allows users with one click to change their cell types. And so you iterate across all your libraries, you find all the commonality, you parse based on name, and you can group them up based on function like XOR 2 is a simple function. Well, that's replicated across all your channel links, all your VT flavors, all of your, and possibly even through all your sizes. And so you can iterate across that, find all the same things, and you just produce a lot of skill code. That skill code is dumped out and used once in the CDF thing of the cadence tools. So the other thing is you copy and you basically create a simple version of that cell. You add another property that's shown on the cell, and then you generate a lot of skill code. And then also, if you use cadence, if you write in this LXU cell property, that will actually automatically work with their layout conversion process. But we were just net listing out, and so you can actually had to get the netlist updater to read that property and use that as a cell name instead. And then once you have all this library data built up, you have your library set. You just remaster all your existing schematics. You write a one-time script for that. And then also, we did this at the same time. It'd be the same thing as doing a technology change. And so we changed technologies, and I remastered for this new mechanism at the same time. Result is 10,000 Stern cells turns into basically 120 different functional symbols. And everything else is in the menus. And then technology changes, you can map more easily because you just go and you change properties. You don't have to change libcell view of cells. And then the users I had just loved that because they love just open it up, click, close. And that was a very simple means of modifying schematics. They said those made them twice as fast at doing that. So this is the level of project of stuff you can just with a little bit of OA script, building your own libraries. If you need help, we have a little bit in the OA script cookbook. I have a little bit in the Python section out there. Haven't been a whole lot of volunteers for the other languages. There's a Doxygen-based API project with Matt Matthews kind of taken over recently. So it's basically like the online C++ docs, except there's four extra buttons at top. You can select any of the programming languages. Feel free to file bugs when you see things wrong with them. We're still debugging. If something's syntactically wrong there, then we'll go and work on that. The OA script source package normally has tests and labs subdirectories in the Python branch. There's a lot of good examples in those. Sometimes we refer people to those. I don't know if the latest version does. When I downloaded it didn't seem to. And then also the other thing, C++ tutorials and forums. There's a big C++ document, multiple chapters. Their forums are probably a little bit more active, and so just about anything is about the same between the languages. If you understand your language and you understand C++, you can map between them. So sometimes the answer has already been solved in C++, or the question has been, because the working group only just kind of maps the language over. They don't really try to change anything about that. So how to should be somewhere between languages. The actual syntax will vary slightly based on the language. And then, of course, now we have a new open access special interest group, which is why we're all here today. So that's all I have. Thank you.
Okay, so my name is Tom Whipple, and I work at Zuken. And today I'm going to be talking about IC package co-design using open access in CR8000 Design Force. So I'm coming at it from a more of a product-centric perspective, sharing with you how we've taken open access and moved from a PCB tool company to a tool that can go chip package board co-design in our flows. So I'm going to split up my talk into three different sections. One, I'm going to talk a little bit about Zuken, give you a perspective of who we are, kind of what our tools are, and where the open access fits in, and how we've used that to provide a co-design solution to expand our capabilities. The second section, I'm going to talk about co-design perspectives. What does it take to do co-design in electronic design? This is of special interest to me. I've been doing co-design in EDA for the last 12 years. I've been in EDA for 24 years. The last 12 has been doing chip package board co-design. And I recently came to Zuken because of the passion that is at Zuken for co-design across the board in all the electronic design. Another motivation I have is I am the chair of the chip package co-design working group at Si2, and I'd like any of you guys to join us if you are interested in co-design and want to join us in conversations about co-design and how to be able to get the industry talking together better in design processes. Okay, so a little bit about Zuken. I say growing up, I've always pictured Zuken as a PCB tool company. But there's so much more than that. There's actually three main businesses we have. We've got PCB and IC packaged product-centric design. This is our layout and simulation capabilities for chip package board. We also have our E3 series tools, which is the harness, cable, and control systems, and then our library and design data management with DS2. I'm going to be focusing on the PCB and IC package design domains. That's where we're doing the co-design. So that's in we'll talk about CR8000. And CR8000 breaks down into four main sections. We have our system planner, which is block diagram capability to plan out your system, including MCAD capabilities. And then we've got Design Gateway, which is our schematic tools. I'm going to be focusing on Design Force. This is our layout tools, which is, like I said, has been known as the PCB layout tools. But again, as I said, it's much more than that. And then we've got the DFSM Center, which provides tools that enables panelization and preparing your data for manufacturing. Again, I'm going to just focus on Design Force. So what is Design Force? This is a multi-domain system design environment that it provides hierarchy that allows you to bring in chip, package, and board design data and visualize that and concurrently implement and optimize chips, packages, and boards in your design flows. It combines conventional 2D design with 3D design in real time, and open access is what has allowed us to move into the IC design space. And I'll get into that more in a little bit. We use the latest user interface technology, so it's just very easy to move around in the design space in 3D, in either 3D or 2D. We can design in either 3D or 2D. And it provides one environment for high-speed design, constraint management, simulation, as well as just standard layout and place and route. All right. So, co-design. What is co-design? Where does it fit? In the past, we've seen in the market co-design tools. You can go out and buy a tool to do co-design. But really, co-design, in my belief, is something that should just be integrated into your system, something that should be almost invisible, that enables you to communicate between the different design phases, the IC team and the package team and the board team. If you're doing fan-out wafer level packaging, how do you manage that design throughout with the package, with the chips, with the ASICs, the chips that are in design or off-the-shelf components, plus the RDL routing and the wafer level layers. In our view, co-design is something that just happens all the time. You got to be aware of what's going on in the neighboring environments, the neighboring components that are being designed. Open access gives us that window into the IC design space and has allowed Zuken to move into that space. So our co-design flow or design flow kind of looks like this. Like I said, we can bring in IC design data through open access. We've got package and PCB design data, which is native in our Zuken tools, but inevitably there's other companies, other EDA vendors that provide these same services. We need to be able to talk, whether it's a Zuken PCB or someone else's PCB, we need to be able to talk between these various tools, and co-design, a robust co-design environment will allow us to be able to do that communication regardless of what kind of design tools that you're using. Now in the Zuken tools, like I said, it's hierarchical. We can bring all of these design portions of the design into one view and easily turn them on, turn them off, make them visible, make them invisible, move around in a 3D design space, see what's happening inside each one of them, and then see what's happening between them and design accordingly. And just one point to make is Zuken is the only EDA vendor. The Design Force is the only PCB design tool that can do mask-ready RDL routing. And that's coming from what's been known as a PCB design tool company. With open access, we can get down to the IC design space and do mask-ready RDL routing. With these design tools, we can do, in one canvas, be able to do any kind of combination of advanced packaging that you want to do, whether it's high capacity, high bandwidth, high pinout. We can bring in multiple PCBs, multiple packages, multiple dies. Each of the dies will be in its own separate open access instance, and design them simultaneously with a vision of the whole system at once. And native support for open access is really what has enabled us to move into the IC design space. So here's a little movie that kind of shows some of what we do with the IC. We'll import a left def. Our layer stack up is exactly what's defined in the left def, or in the left file. And then we bring in the def file, which we can see the floor plan of the IC. So if the IC team has already done some design, we bring that in. And then we can synthesize an I/O ring. And not only I/O ring, but area I/O. We can put our I/Os wherever we need to put them. We place the I/O cells, do pin assignment from the I/O cells to bumps, and then our RDL routing. RDL routing is both automated, and we have manual RDL, wire editing as well that supports that. We then take those results from the open access database and drive the pin out to the package, or in this case, we're going to bring in a fixed pin out from a board team, which is there's a ball map format. We'll bring in the ball map, and then we'll see that the rat's nests are not where we want them to be. So we will optimize the placement of the IOs, the net assignment to the bumps, and correlate what's going on in this fixed ball out and this fixed die core, and map those accordingly with the IO pad ring and the bump arrays. So that's kind of a very high-level view of what we do. And I don't know if you could tell as we're going back and forth, when we go into the open access view to design, our layer stack up shows what's in the left. Okay, we switch into the open access context. It's all the technology, constraints, rules, layout, and the design is open access. When we go into design in the package, with the click of a button, I don't show the hierarchy browser up there, it'll come up later. We click into the package context, and we immediately switch to the package stack up. Package rules, package technology. So we can just very readily, easily, with the click of a button, move into the technology space of each of our components. And we have some databases, some examples from customers, where we have 9 different components. We'll have a couple of ICs, a couple of packages, 2 stack-ups, interposer on a board, maybe with like a battery board coming on top of that. So very complex, but it's very easily managed because each of the components is managed in its own space and context. So what is necessary for a robust co-design? And as I talk about this, of course, everything's in the context of Zuken because that's who I am, but these things are relevant across the industry, and that's kind of in the Si2 context. When we get together as the chip package co-design working group, we want to talk about how do we get the mentors and cadences and Zukens and synopsises and answers and talking together so that we have much more smooth integration of tools, no matter what tool sets you're using. So I've come up with these components of co-design that I think are necessary, and anyone who wants to play in the co-design space should adhere to these types of things. First of all, you need a hierarchical design environment with 3D design capabilities. Well, that's not really a hard requirement because most of the tools in the industry don't have this, but they still can share data. But this makes it a whole lot easier. If you have this, it's easy to pull things together. A 5-die wire bond die stack on a package. It's much easier if you can pull things together in a hierarchical design environment and look at it in 3D. I've done it in 2D. It's possible, but it's a royal pain in the backside. Okay. Net mapping. Every design space is going to have its own namespace. And so we need to manage that. You need to have cross-component awareness in the various design operations. Standard design exchange formats. This is one of the places that we talk about in our working group. What formats are needed to be able to bring this data together and share data between the various design tools? And of course, open access is a big part of that. You need a clear definition of what's going to be visible and what's going to be modifiable. Got to filter out unneeded data because there's a lot of stuff out there that you don't need in the core of the die when you're doing chip package board co-design. And you need a difference viewer and ECO mechanisms. So you have these things in each of the design tools, you'll be able to much easier communicate and collaborate. Okay, so let's talk about each one of those. Hierarchical design environment with 3D design capabilities. This is just a simple movie that goes into 3D mode. You can see how easily we move between 2D and 3D modes in just a moment. We're going to take a little component on this package and drop it down and embed it in one of the substrates. Okay, so having things in 3D just makes it much easier to move around and kind of see what's going on and do your design. Each hierarchy, as I mentioned before, defines the design space, the namespace, the coordinates, the netlist, and layout, the layer stack of the technology and the design rules for that part. And it's going to be different for each part. It controls the visibility of each device. So you can, if you got a 5-die stack, you turn off the top 2 and the bottom 2 dies in the stack and look at the middle one and see what's going on. Or you can turn on the middle 2 and see how they're relating to each other. And then you can move that visibility around very easily. As you can see, we're going in and out of 3D easily, and it's very easy to control that visibility. As we change the focus, as you just click into each of the parts, it changed the context into the design space layer stack up and rules and namespace of that part. Net mapping, I mentioned before, is critical to do properly, because if you've got a 5-die stack on a package on a board, or a fan-out wafer level type of design with multiple dies and a pop on top, you're going to have different names for the same signal depending on what space you're going into. Design Force gives you the ability to map between those. You go into 3D, click on a net, regardless of what context you're in, it'll follow that net throughout the stack, and you can see where that's going and what's happening to it. You have to logically map between these spaces. The LSI net might be data 1, package net might be D1, PCB net might be PD parentheses 1. Those all map together. You need a tool that Design Force does that mapping between those spaces. So when you're working and popping between them, you can always know which net you're talking about and be able to cross probe and analyze accordingly. Cross-component awareness in design operations is critical. As you're designing features, you need to be aware of what the effect of that command is going to have on neighboring components. For example, in this case, we've got a package on package, and we've got a couple of nets that we want to do some net swapping. We've got the orange and we've got the blue pins. And down here at the bottom is one component, up here at the top is the other component. We do a net swap here, there sure better net swap sure better happen down here, or else you're going to end up with shorts that you don't want. Okay, so having functionality that allows you to manage that, that understands the connectivity and the relationships, physical and logical relationships on the devices in the neighborhood is critical. Net swaps might cause, or they might fix crossings in adjacent designs. And that's, again, it's really nice to have a co-design environment where you can see the chip and the board simultaneously, and see the chip into not just the bumps, but the RDO routes and the I/O pad ring as well. So you can optimize from a connector on a board to a BGA or a pin out for a fan-out wafer level design into an IC and have a very smooth routing path to improve your routing capabilities, lower your layer count, give you better SI performance. So speaking of performance, we have this example from Toshiba in which they're using Design Force. They have a multi-component system, and this is a communication device that they're putting into a cell phone. And as they're shrinking it down and working on putting it into their analysis of the system showed that there was some spurious noise happening. And as they used Design Force and the analysis capabilities to be able to narrow it down to this particular system of nets, and found that if they changed the layout as such, they were able to eliminate or minimize the spurious noise that was happening. They were able to successfully release this product. So we talked about standard data exchange formats. In Design Force, we use open access. It doesn't give us everything that we need, but it does give us a seamless view into and edit capabilities of the IC from within this traditional PCB design tool. We do use left-def. There are cases where we've got customers with really huge ICs, and we want to bring in just the I/O pad ring, the bumps, and RDL. Open access, we don't have a way at this point to strip that out. At least on their side, we don't have a way because it's not our tools. But we are able to use DEF to strip out the core. The tools that they're using has a no core option when they export the DEF, so that we can bring in the DEF from the IC tool, and then as we read that, the left DEF, then we form our own open access database to do our IC design at that point. Important, another aspect is ECO back to the IC tool. So we don't have full IC design tool. So we do open access down to the I/O drivers. We're using open access. Now when we make changes in Design Force on the pad ring, the bumps, RDL, we need to pass it back to the IC design tool, which is owned by one of the other EDA vendors. Okay, so we typically will do that, we'll either give the open access database back, and they can use it as is and build from that. Or if they need to do ECO back into an existing design, we'll dump out a DEF file. And it's many of the tools have ECO DEF capabilities that they're able to read those changes back into the IC design tool. We also use the JADA LPB or IEEE 2401 format for various operations in the flow. It is made to be able to define a full system, whether it's IC package board and the connectivity between. We only use it for design comparison and non-LSI data exchange in our design flows. Okay, what's visible, what's modifiable, and what's not needed data? Typically in a chip package board co-design flow, you don't need the core. And so we will strip out left library elements that are not referenced in the design, because there are some very huge left definitions out there, and that will bog down any system. Some of the left libraries are huge. So we'll strip out library elements that we don't use, and DEF, as I mentioned earlier, can be used to filter out unwanted core data. And so it makes it for a very lightweight implementation. And then when you're doing LSI package co-design, you will need to decide what are you going to allow to change. Most people will typically just allow you to add and delete bumps and do net assignments to those bumps, power and ground net assignments to the bumps. But there are some flows that are in use today where they will do I/O placement, create the I/O pad ring in the context of the package, and do the bump assignments and the RDL routing in Design Force. And the advantage of doing that is, one, you do it in the context of the package and the PCB, so you have a much better physical and electrical solution because you can design down to the I/O drivers of the chip. When we make changes to the open access database in Design Force, we have a difference viewer. This is an important part. If you're going to do, whatever tool it is, if you're going to bring in modified data, you should have a difference viewer that says, okay, this incoming data is this, your existing data is this. Do you want to allow these changes? We provide that in Design Force as we pull data into open access. And other tools, if they're going to implement a good co-design solution, should have something like this. And that's just all part of the ECO mechanism, being able to identify what you're allowing to change and provide a seamless process. Open access gives us that to be able to update those changes as data goes back and forth. So how do we use this in Design Force? Let me just kind of step through. I showed you a movie earlier. Let me just step through each of those steps that they showed in the movie, and then I'll wrap it up. First of all, one of the key parts of this is it is bidirectional in how we design between the die and the package. IC I/O design can be driven by the package requirements, or vice versa. We can bring in a fixed die and drive out to the package. We'll import an IC from left def, or you can create an IC from scratch, and then that will create an open access database from these steps. And then we'll add an I/O pad ring. We'll synthesize bumps from hard macros and create and arrange the bump tiles. We'll do net assignments from the bumps to from the I/O drivers to the bumps, and do the automatic RDL routing, and provide also wire editing capabilities for manual edits. And then open access databases added hierarchically to the package design. The net assignments from the IC to the package are completed. We'll do fan in and fan out routing, and then optimize from the die to the package or from the package to the die. Then we'll transfer the OA database or a def file back to the IC team. So this movie shows our bidirectional optimization. We have a die down here with some fan-out routing, and we have a package up here with some break-in routing from the ball array. We're going to optimize from the die to the package in this case. In this case, we're going to optimize the net assignments from the package to the IC. So we'll change the net assignments on the IC. Now it will affect the net assignments in the IC itself. We'll check the differences. As I mentioned earlier, this will bring up the differences between the package database and the open access database and give us a chance to accept or reject these changes that we've shown. And we can view and edit the IC bumps and RDL routing in 3D. This gives us an open access view. These gray lines are the open access RDL routes, and the bumps are the gray bumps. The purple are the package bumps, the landing pads, and the escape routes. So you can have just very easy have an OA view and package view at one time in 3D and see what's going on in your design, and you can go in and actually manually edit things, or if you need, in either 3D or 2D mode. So in summary, Zuken has taken advantage of open access to bring IC database into the PCB design tool, and provides our customers the ability to greatly reduce their tool costs by doing the I/O pad ring development in a much lower cost PCB tool set rather than the high cost IC design tools. We eliminate the manual data exchange between chip, package, and boards with a unified co-design environment, but we also do provide support for standard data exchange interfaces, so we can share data with other vendor tools. We optimize I/Os across the domains through hierarchical design environment. And then we conduct feasibility and implementation of any package integration technology, whether it's simple wire bond design or complex SIP or fan-out type designs. We can intelligently design and exchange the chip and interposer bump placement and RDL routing. And then the 3D design environment just gives us an easier way to check for DRCs and shorten our design cycle times. So this kind of collaboration between the various design tools and between our tools and other vendor tools makes for better collaboration and helps what we've seen, people be able to reach their design goals much quicker. And that concludes my presentation. Thank you.
And even though the chip package co-design efforts are not new, we still need to have a lot of agreement on the standards and the data standards for creating the data and being able to exchange it. And that's kind of what a SIG can do for that particular group. So the SIGs that we're working with right now, and we will probably end up we're capable of supporting 4 of them, is the power users, OA script power users SIG, like Corey is working with. The troublemakers, yeah. And in fact, that might be get the T-shirts with troublemakers. The Open Access Virtuoso Compatibility SIG and the Pdk Users and Developers SIG to explore PDK-related topics. Again, the script thing SIG is about using OA script, and we're looking for CAD engineers and EDA engineers as well as designers. And so there'll be, part of this will be creating more users, teaching people how to use this stuff, as well as creating prototypes for implementation code. The compatibility SIG is mainly virtuoso CAD engineers and senior analog designers. We want to prove out that you can use these things and extend the capability of OA script, as well as support the virtuoso-based designs out there, which there are plenty thereof. And finally, the Pdk Users and Developers SIG, and this is, we're looking at CAD support and Pdk engineers, looking at prototyping different methodologies, enforcing the standards, using the standards. I talked about that in my workshop, and you know, being able to bring new tools in very quickly, and going back to the EDA vendors and saying, okay, give us this, you know, what information do you need, and you give us this little thin slice of a writer, and we can give you that information in whatever format you need. So, SIG, sign up for a SIG if you want to work with experts or you want to become an expert. And you know, everybody can contribute. I've spent my career learning from everybody else. If you have an issue that you have that hasn't been discussed, we don't yet have a 3D packaging SIG, but Tom brought up a whole list of issues that need to be discussed not only by users but by EDA companies. So he may go, let's form a SIG. It's a little looser than a working group because it can address a much wider variety of issues. And of course, your company needs to be a member of Si2 to start up a SIG or to be a member. So that's the website. Any questions? All right. Well, thank you very much for spending the afternoon with us.